And I think the recording has started. So, howdy. So, first off, we have Mike Pilquist. Uh, Mike is a longtime member of the Type Level Steering Committee and author of a lot of our important libraries like FS2 and SCODAC. And most relevant to this talk, Mike wrote the second edition of the Red Book, Functional Programming in Scala, bringing things up to today and the current version of Scala. So let's all welcome Mike on the stage and give him a big round of applause. And
Thank you.
take it away.
All right, let's see if this works. All right, we see full screen? Let me know in chat if not. All right, so thrilled to be here and excited to give a talk on the work I was doing on the Red Book over the last couple of years. For those that maybe lost track, it felt like the book came out recently, but it was nearly a decade, and it was over a decade if you count, the time it was started by Paul and Runar, and then eventually published. A lot of folks ask what's different in the second edition. Like a true programmer, the book is written in ASCII doc, not in Microsoft Word. And I have a Git repository with all of the changes to the book. So in preparation for this talk, I did a Git diff and looked at the distribution of changes across chapters. And one of the maybe obvious things in hindsight, but interesting things is that earlier in the book, there's less changes. And as we progress from sort of the introduction of Scala syntax, the introduction of referential transparency and immutability, and then recursion, and get more into applications of functional programming, and then eventually the abstractions and the structures that we find in functional programming, more and more has changed. And so in this talk, what I'd like to do is sort of walk through some of the ways in which Scala has evolved from the point where we were a decade ago, and then changes that were added to the language, both in Scala 2 and then subsequently in Scala 3, and look at sort of where we are now in 2023. So when I give a talk like this, I always like to start with semigroups and monoids. They're my favorite type classes. They're actually what got me hooked into functional programming in Scala. There was a Scala I believe, in Philadelphia that I missed. I wasn't able to attend. And I saw all of the chatter live as it was happening. And I felt very left out and very sort of interested in this functional programming space. So I started watching some videos and got hooked, and really liked the idea of sort of type class composition. So I wanted to start by looking at how we will represent type classes in Scala 3. I'm not going to talk about like type class laws and sort of the key ideas behind each of these type classes. I rather want to look at how we encode these concepts. So if you're familiar with these, or if you're not familiar with these, bear with me. This is more about like the syntax and the encoding than it is the actual type classes themselves. So we have this semigroup. Semigroup has a single abstract operation, combine, which takes two values of type A and returns another value of type A. And we have this monoid that extends semigroup. Relatively straightforward code, short of the lack of braces. This looks like regular Scala 2. So the first thing I want to do that is perhaps unique to Scala 3 or is new to Scala 3 is defining an operator for combine. So we'll define the pipe plus pipe operator. And we'll define that as an extension method on an arbitrary value of type A, here called X. We're defining this extension method directly as like a member, as a concrete member of the semigroup trait, right? And furthermore, we inline this definition so that at call sites, right, the compiler just inserts calls to combine instead of going through the indirection through pipe plus pipe. right? So we have this like guilt-free way to do operators, right? We don't have to pay any syntax tax. We don't have to pay like object creation or deal with like kind of complicated any-val patterns or import tax, etc. We can just put this extension method directly in, as a member of our type class, and then inline the definition of the operator. Let's take a quick look at how we might use that. So here we have a definition or an instance of our monoid type class for integer addition. We declare that as a top-level type directly in this leopards package, right? Or top-level definition. We just define it as integer addition. And then at a use site, we can just import all of the givens out of the leopards package and immediately start using the extension method, right? So we're not importing like semigroup.given, although we could have. Rather, because we import leopards.given, we're picking up this int addition monoid instance, and that monoid instance is providing us that extension method. So there's a whole interesting set of things we can investigate here around like library design and where we put our extension methods and our givens such that our end users have the best possible import experience. So let's keep going. We can define type classes inductively, right? So here is a typical definition of a monoid for option of A, anytime A itself has a semigroup instance, right? And all this monoid does is says when both values are combined, then we'll return, or sorry, when both values are defined as a sum, we'll return the combination of those two values. And in the other cases, we'll return either the defined value, or if both are undefined, just return none. Right, so we can define these inductively. And here, the A parameter to the option monoid given instance takes that semigroup instance as a context bound. Usage works much the same, right? We can import the leopards.given with that same import. We pick up the extension method through this option monoid given instance that we've imported. So let's do a quick rewrite. And I'll toggle back and forth a few times. If we expand the context bound into a using parameter clause and give that semigroup instance a name, $SA, then we can look at how the compiler will inline the definition of our operator. Right? It's just going to call $SA.combine, essentially. And if we looked at bytecode and sort of worked backwards from there, we'd see that there is no overhead from that operator. So let's keep going. We can build a monoid instance for maps. So this would be for an immutable map from values of type A to type B. And the implementation here is not entirely important. The fold left, the implementation of combine that is. The important idea here is that this monoid for maps is going to merge the entry sets of the maps. So the key sets are the union of the key sets of the input. And if two maps have a value at the same key, then we use a monoid or the semigroup instance to combine those values, right? So the output map at that key has the combination of the values from the input maps. And again, we can take this semigroup instance as a context parameter. Here in the implementation, we are using the option monoid we just defined, right? To say like, hey, whatever the value is, if it's defined at this one input key, give us that back as an option, and then combine that with the value from the map that we're folding in. Right? So now we're layering these semigroups one upon the other. We can do the same rewrite. So convert that context bound to an explicit clause, name the parameter. Here we named it $SB. And then we can expand and look at sort of the manifested monoid instance the compiler is inserting. And so if you work through all the types, I don't expect you to do that in your head, like as we sit here, but as you work through all the types, you end up with this expansion. In essence, the compiler is going to assert a call to the option monoid given, passing this semigroup of B as the dependent type class instance. And then insert a call to combine, again, inlining that operator on that instance. Okay. We can also define extension methods using these type class instances then. So if you know cats, you probably are familiar with the combine all operation, right? So on any collection, and we'll talk about that in a little bit, but on any collection, we can define this combine all operation, which just folds all of the elements of the collection, starting with an empty value for the monoid, and then they're just combining pairwise. The interesting thing about this combine all here is we can define it as a top-level extension method in our functional library we're developing, right? And here we define it for any iterable once. We can define a similar operation. So if you're familiar with fold map, it's sort of like combine all, except first we're going to map a function over each element of the collection. That mapping function will return some new type B, and that type B is what must have the monoid to do all the combinations. So by defining that, or those concrete extension methods at the top level of our package, then again, with that single import leopards.given, we can write code like this. So this function bag computes an occurrence map. Basically it says for every key in the map, the value represents the number of times that key showed up in the input collection. And one way to compute this is to say, call fold map on this input collection and convert each element into a map with that element mapped to the number 1. Okay? And then as all those maps get combined, we end up with a union of all of the keys. And we use the semigroup for the value, in this case, a semigroup of int, to add up the occurrences. And you can see in the example here, if we pass the character collection made up of the string Scala, we get the expected result with SC and L mapped to 1 and A mapped to 2. So what's interesting, again, is maybe not the algorithm itself, but the rewrite. So if you think about the monoid that's being derived, in a sense, you end up with something like this. Like the compiler is able to look at the fact that the inner function we're passing to fold map is returning a map of A to int, and it goes and searches for a monoid instance for a map of A to int. It finds our map monoid given and realizes that, hey, in order to materialize this monoid, we need a semigroup for integers, and goes and finds the int addition monoid. And then, of course, in between those two, it's actually using that option monoid that we developed to actually do the combinations. So this might seem rote, like we're maybe used to working with inductive definitions of type classes, right? But it's worth pointing out, in the Red Book, there was no passing of type classes implicitly whatsoever. Type classes were instantiated as values and then interacted with directly. If you wanted to fuse together a bunch of monoids into a more powerful monoid for a more complex type, you wrote that code by hand, right? So 10 years ago, that was sort of where we were. And we were experimenting in different ways, right? With different encodings of type classes. And it was really Scala Z7 and the type class encoding there that sort of sent us down this path of, at the time, using the implicit machinery to do type class manifestation. The other thing to point out here is that type classes in Scala 2 required a lot more machinery. And so if we wanted to write semigroup in Scala 2, one way to do that was to use a project I created a while back called Simulacrum. Simulacrum came about because I didn't like all of this machinery that was necessary to describe these very, to me, simple and elegant ideas around type classes. When you added all the machinery, it obfuscated the important parts of the code. And so we wrote Simulacrum. It was a macro annotation. And the idea was that you could just annotate a trait with @type class, and we would just auto-generate everything else for you at compile time. So this example here, if you say @type class and put it on this trait semigroup, what Simulacrum actually generates looks something like this. And there's more. Like, it's intense, all of the things it must generate. But all of this cruft is really just about getting the right import experiences and getting the right mechanics to let us kind of assemble all these type classes into a large functional programming library. All right, let's look at a few more. Again, I'm not going to talk about like type class laws, and I'm not going to introduce the concepts of like functors and applicatives and monads today. Rather, we're going to breeze through some syntax just to see how this stuff like looks different in Scala 3. So here we have our functor type class. Functor is parameterized by a single type parameter f, which is a higher kinded type, right? A type constructor of a single argument. What's different in Scala 3 as opposed to Scala 2 is that we would define the map operation as an abstract extension method, right? So we're saying all of these first three operations are all extension methods on some f of a. Map will be defined as our key abstract operation that implementers of functor are going to have to implement. And then we can also define our derived operations like as and void as concrete extension methods using map. So the key idea here is just that extension methods can be used just like regular methods, right? There's nothing special about them such that like they're limited just to writing operators. Applicative functors, much the same, right? So here's an example. Applicative functor, we define a pure operation as an abstract top level, direct method on the trait. And then we define a map2 operation as an extension method on an f of a. These extension methods might feel gratuitous if you're used to working with the Scala 2 encodings of these type classes. But one of the things that sort of shifted from 10 years ago to now is that we developed our own Scala style, right? We took like the object-oriented modularity code organization techniques and applied them to functional inspirations. And so the idea of like, well, everything's just a top-level function where you pass methods to faded into the background. Instead, we said like, we're really going to adopt this dot notation, right? So anyway, we can encode that dot notation directly here without building that separate syntax or ops layer that you see in today's functional libraries. Extension methods are just like regular methods. So just like map2, being an abstract operation here, we can define map as a concrete operation, providing an implementation from the abstract map we pick up from functor. We can extend this to monads. In this case, we'll just define flat map as our single abstract operation, and then define both map and map2 in terms of flat map and pure. We can define foldable functors, same idea, right? Rather than providing syntax like fold map for just Scala collections, we can say any type constructor that has a foldable instance, we can provide you a fold left, fold right, and fold map extension method. And in this case, you can see fold map is using that same monoid syntax from earlier. It's able to use the pipe plus pipe operator because that monoid of B is available in as a contextual parameter in the body of fold map. And we can put all these together and start using more complex, higher kind of types, right? So here, the traverse type class extends both functor and foldable and defines traverse as the key abstract operation, picking up an applicative instance for some type constructor G. And then similarly, sequence can be defined directly in line as an extension method on an arbitrary FG of A. Right, so if you're not familiar with these type classes, don't worry about it too much, but the key idea here is that extension methods really take away a lot of that mechanical overhead that we were using to encode type class hierarchies in Scala 2. And a great example of that is this snippet from chapter 12 of the book. And so chapter 12 introduces the notion of applicative functors and traversable functors. And there's this example where it traverses an f of A with the state data type, the state monad, to implement the zip with index functionality. And it's sort of a beautiful example of how traverse is just this, Swiss Army knife of functionality, and you combine it with other interesting types to really get some really interesting behavior. But before we can even introduce the implementation, we've got to say, like, hey, Scala can't quite figure this out, right? The type inference is not quite good enough. The type system doesn't quite let us talk about the types we want to talk about. There's all of this incidental complexity leading to things like type lambdas and issues with inference and having to pass, type class instances explicitly, etc. And it sort of like takes the legs out of it right away. Like, hey, there's this really beautiful concept, but we're not quite there yet. And the really neat thing is with Scala 3, all of that just evaporates. Right? The type inference is better. The type system is better. The extension methods are better. Like everything just sort of slots in. So this is a diff from that part of the book where you can see the natural implementation just works. And so my key message today is really that functional programming in Scala 2, it was really like a meta language. And what we had to do, right, was take these concepts we had in our head, like type classes, and then compile them down to Scala 2 just to kind of get it all to work. And then folks would look at that code and then see like the mechanics and not see this higher level language we're actually working in. To back that up a bit, these are just some of the things that became essential over the last decade to write functional Scala at scale. And in the Scala 2 column, it's the infrastructure that we built, either as part of the open source community, as part of ePFL, et cetera, to address the gaps in what Scala 2 could do. And to be fair, this was Scala 2 a decade ago, right? And then all of this functionality got built in slowly, maybe slowly or slow enough at times that it was sort of like a frog in a boiling pot of water. We didn't really appreciate the improvements we were getting as we were getting them. I want to do another example of what I mean by that. And so here's an example of applicative, sort of applicative composition. Like we have a bunch of effectful values. Maybe these are like ethers or validated values or whatever, but they're a bunch of effectful values. And in Scala Z, like if we had 3 of these, and we want to sort of put them all together and work on the inner value here, we would use this pipe at pipe operator, or as Bill Venners used to talk about, like the scream operator. For him, it was reminiscent of the mask from Scream. In Scala Z, this was implemented with a series of boilerplate. There was these applicative builder traits, and each applicative builder trait, like applicative builder would call applicative builder 2, and applicative builder 2 would call applicative builder 3, and so forth. I think initially it supported like up to 6 values, then someone PR'd a bunch of boilerplate to get it up to 12 consecutive values. Point is that the language didn't have the mechanism to talk about this pattern in a general way. So when we built cats and we founded cats, one of the ideas behind cats was to really sort of adopt this Scala style, to say, we don't want to just inherit ideas from other language communities, be it Haskell or be it OCaml or whatever. We really want to define our own style. And in this particular case, what we decided to do was say, well, why don't we just create a tuple of all those effectful values? And then we can define a map n operation, which just is a function, in this case, a function of 3 parameters, function 3 to some output value. And we can sort of do some management there of handling the tuple, in this case, a triple conversion into the input to a function 3. And so this is the syntax we ended up coming up with. This is what I'm sure many of you use in day-to-day code. This is not quite, or really not that much different than the Scala Z implementation. The only interesting thing here is that the equivalent of those applicative builders happen to be generated at compile time, as opposed to someone like copying and pasting the builder types into a Vim editor. There's just a boilerplate generator integrated in the SBT build, and it generates up to 22 of these sort of builder patterns to make this stuff compile. So in Scala 3, we now have the capabilities to write this map n operation in a general way. And I'm not going to get into all of the details here, but we're using a few key ideas. We're using the fact that we can abstract over the arity of tuples. Okay? We can sort of do what Shapelist did with HLists, but now with tuples at a type or from a type level perspective. Again, the types here are not particularly important for today's talk. The idea is that both mapn and tupled can be implemented in a sound way and give us the types we expect without generating boilerplate for every possible arity. For completeness sake, there are some implementations of the tupled and mapn operations in the slides here. I'm not going to go through them in detail. There's one implementation that is relatively efficient, that the compiler is not quite able to reify all of the different type equalities that we're relying on in the implementation, but nonetheless, this is a sound implementation. And there's also an implementation that can be reified, that has no casts, that works just as well, but is a little bit less performant. So then the question becomes, if this is also great, what about cats? Should we take these ideas from this leopards package we've been building up in this talk and turn it into the next version of cats? And for me, what that really comes down to is this. The first line is what we have today when using like cats2 with Scala 3. We have this import, cats.syntax.all, and it gives us all of the derived operations, all of the syntax we need to call things, like call map on an arbitrary f of a given a functor. We've already moved all of the given instances in cats, right, to the appropriate places in the type class hierarchies, so that you should never need like a cats.implicit underscore import anymore. And you should never need to like import a direct instance anymore. And so while the cats code base could really become maybe much more clear, right, or much clearer from the adoption of the Scala 3 functionality, I'm not convinced personally that the benefits for folks reading the cat source is worth the ecosystem breaks that would occur. And there are some other some other improvements, especially around performance, that we could use inline definitions, and we could avoid some allocations in certain cases, or at least make those allocations much easier to avoid. So I don't mean to downplay that too much, but at the end of the day, we really have to weigh the stability and the level of the ecosystem that would be breaking, and look at it, in comparison to the benefit we get. So wrapping up, when I look back at the last decade, one thing I thought that was kind of interesting was to look at it through the lens of like the Tuckman model of team formation. So if you're not familiar with the Tuckman model, it's a team and sort of organization analysis model that was built in the 1960s, really about how like teams come together and when they become effective and performant. And the four key phases are the forming phase, storming, norming, and performing. Later on, they added a fifth phase to the model to represent like the adjourning part of a team, like when a project is done and the team sort of disbands. But anyway, I think it's interesting to look at functional Scala through that same lens. And in the early days, we had this forming phase where we were bringing in ideas from Haskell, and we were bringing in ideas from Ruby, and bringing in ideas from enterprise Java, and everybody had a different opinion of how things should come together. No one was really sure, quote unquote, who was in charge. There was a lot of uncertainty and a lot of ideas. We went into this storming phase where leadership started to emerge. Folks became principled about the things that they were looking for out of the language. There was a Northeast Scala in 2016, which I would say is right towards the end of the storming phase, where some of the key elements had been founded, right? People were writing books about cats and books about shapeless, but putting all of those pieces together into an actual useful application was very painful. That was the main theme of the conference, was like, there's way too much glue code for everybody to write to do useful stuff. So then from like 2017, maybe up through like 2018, 2019, we went into this norming phase, is the way I look at it, right? We went key infrastructure like CATS and CATS Effect and FS2 stabilized and became safe for people to build the next level of middleware on, right? And then there was like things like HTTP4S, were built on that. Doobie was built on that, Skunk, etc. And then third tier middleware that built on top of those libraries were able to come about. And of course, all those projects existed this whole time, but the stability was the key point, right? That to go and use these things, you weren't chasing down different versions of different libraries and writing your own glue code and so forth. And then finally, I argue the past 3 years or so, we've really been in this performing phase where now you can just pick up these tools. You can be productive right away. You've got cross-platform support. We're really at the cutting edge of concurrent application development on the server side. And then those same concepts, those same libraries apply just as well to JavaScript applications, both client and server, as well as native applications. Of course, there's changes coming. There's always going to be the next big thing, and whether that's direct style syntax or the research Martin is working on, or shorter term things like Loom's virtual threads. At the end of the day, there's always going to be changes coming. And so I'll leave you all with this quote from Daniel. This is from the foreword to the second edition of the book. I won't read it, but the general idea, when you look at where we were a decade ago and you look at where we are now, we really forged the functional language that we wanted. And maybe not totally intentionally, right? But we built up all of these mechanisms, influenced the language designers, influenced the evolution of the language, and built the thing that we wanted. Who knows what it's going to look like a decade from now, right? But I do think the investment we've made in some of these key ideas will continue to pay off, even if the syntax changes. So anyway, that's all I had for today. I know I'm a little bit over, so happy to take questions in chat.
Thank you, Mike. That was fabulous and really kind of inspiring.
Thank you.
I will stop the recording here.